We're talking about threaded fasteners, okay? And in drawings, you know, when you see threaded fasteners in drawings, there's a few different ways that you may see them represented, okay? So this is kind of an example of how you might see some threads. Now, this is on a bolt, right? But you might see the threads shown as detailed, like in the upper left corner, where you're actually seeing the thread forms, okay? Or you might see it as schematic, like shown down at the bottom, where there's just long lines. And with a short line, you know, they're all centered along the axis, but one goes all the way across the cylinder and then the shorter one doesn't, right? So that's called schematic thread representation. But the most common way that you'll see this on drawings, and the way that I'd like for us to use, is simplified representation, which is in the upper right corner. So what we have here is a bolt, right? And from here, this way has the threads. And the threads are just represented by this hidden line inside the object line here. So, right? Does that make sense? And that hidden line is representing what? What do you think that's representing? It's actually the valleys, right, of the thread form itself. Okay. So does everybody kind of understand what I'm saying when we might see this three different ways? You might see it like this, in one way or the other. So if it's detailed on external threads, you'll see it like this. And if it's detailed on internal threads, you know, if you're looking at it from the profile view, you'll actually see the thread forms. And if you're looking at it from, you know, in this case, the right side view, which is where the hole is actually at, right? The left side over here is all hidden lines. So we've got the solid material between it and the hole. But this is real important. What I want you to understand too is that we have a solid circle, and then we have a hidden circle on the outside of it. So regardless of the way the threads are displayed on the drawing, detailed, schematic, or simplified, this is what the hole is going to look like from the top, regardless of the way the threads are looking. You know, the threads may be shown a little different way in this view, but regardless, they're always going to look like this. Okay. So again, you know, these circles are really representing what's called the minor and major diameters of that thread form. Okay. Does that make sense? So we've got, you know, some terms that go along with threads. We've got the crest and the root, which are really what those circles are representing, right? They've got an axis and everything, and some other terms that you might see, which is kind of more commonly used, in my opinion, that's easier to see: major and minor diameters. And then the pitch is an important term. So the pitch is the distance between each thread form, and that's a major specification in the type of thread that you're using. So that's an important concept. And also, the pitch is equal to, on a single thread form, you know, if you take and revolve that fastener one revolution to the right, it moves, the fastener should move into the hole, whatever that pitch value is. So the pitch is equal to what's called the lead. The pitch diameter is where the internal threads and the external threads, actually the average of where they meet. It's kind of the central line of where those threads engage one another. Most of your single thread forms are 60-degree thread angles. It's the most common. Most common are right-handed threads. You know, if there's no specification about whether it's right-handed or left-handed, we always assume it's right-handed. If it is left-handed, then we need to note that. And what that means is, you might have heard the, you know, righty-tighty, lefty-loosey thing, all right? Well, that only works on right-hand threads. If you got a left-hand thread, then you'll have to turn it to the left to tighten it. So just keep that in mind. They rotate different directions to advance or withdraw. There are different types of thread forms. So typically we'll see the unified 60-degree unified, which is kind of this one right here, or American National, or just the Sharp V. Those are your common threads. There's some specialty threads like the Acme or square threads. Any idea? Well, first of all, you see the knuckle thread there. Have y'all ever seen any knuckle threads on anything? Brass knuckles? Is that what you said? Yeah. They got threads on them? Huh? No, but I mean, yeah, I don't know. I haven't seen any brass knuckles with any threads on them. So you'll see this on the base of your old school incandescent light bulbs. You know, the threads and the sheet metals and those type of fuses that screw in like that. You'll see those a lot of times in sheet metal objects that are pressed. The threads are pressed into them. Acme threads. So an Acme thread, notice how thick that thread form is, and there's a lot of there's a lot of area of material in there. So if you look at it versus the 60-degree thread, it can push a lot of pressure, right? And anybody think of anywhere where they might have seen the Acme threads? That's the kind of threads that the Coyote's always dropping on the Roadrunner, right? Y'all have never seen the Roadrunner, have you? I have. Okay. All right. But you see those on bices, and if you look at the 3D printers, a lot of those things that are moving those platforms up and down, that's going to be an Acme type thread. So it's designed to put more pressure on. You know, if you put a lot of pressure on that 60-degree thread form, what's going to happen? It'll strip, right? You'll just pop the threads right off the cylinder, and now you got a big mess, right? So these Acme threads or square threads, those are designed to apply a lot of pressure. Now, if you're working in Inventor or even some of the other packages, a lot of those packages might not have the Acme screw threads in the thread bank, right? It might not come packaged in the software. And in that case, don't panic or don't get too concerned, right? Which way did I say we wanted to represent our threads? Simplified, right? So that's just got the solid line and the hidden line. So what you do is you just put any thread that fits on that size cylinder on there, and then in the drawing call it Acme threads like you're supposed to. Does that make sense? So you might not be able to actually model that particular thread in there, but in the drawing it's just going to be a series of hidden lines and solid lines that represent the threads. It's a symbol for threads, so it doesn't have to be the exact same shape. You just put the note on there right. You'll also see buttress threads. The difference between a buttress thread and the Acme thread would be that the buttress thread is designed to push in one direction only, where the Acme threads can push in both directions. Some other specialty type threads might be for, piping systems. They use what's called a national pipe thread, which is a tapered thread. So you notice how both the internal and external threads are tapered in to help seal better for liquids and gases. Those NPT threads are usually built into your CAD software, so those are there. So when we talk about inch type threads, or really any type threads, you might hear the term coarse, fine, or extra fine. Okay, and that's controlling how many thread forms there are per inch. So the more thread forms there are, the finer the thread is. And you can kind of see that moving from left to right on this example. You have the coarse threads, and you can see they're big and fewer of them. And then you get the fine, they're smaller and more of them. And then you get extra fine, they're even more smaller and more of them. So, typically you have coarse, fine, and extra fine threads per inch designations for each size thread that you have, right? So you might have a 1/4 20 that's coarse, or you might have a 1/4 28 that's fine, right? There are also what's called constant pitch numbers. So they may regardless of the diameter, they may have either 8 threads per inch, 12 threads per inch, or 16 threads per inch. And that's why when you take your bolt to the Lowe's store and you try to find a replacement for it, they got, that big plate that's got a whole lot of different options on it. You just kind of have to figure out what you got. So you have to match the diameter and the thread series for the pitch. So when we specify threads, I apologize for that yellow. That's hard to see. I didn't notice it, or I would have fixed it. I noticed it on the metric one. We've got 0.75-10 UNC 3A-LH. So what I'm really needing you to understand is, what do those digits mean? And I need you to understand that's what you should see when you specify threads on your drawings. Okay, these are inch threads. So the 0.75 is the nominal diameter, right? If I take the dial calipers and measure it, it might be 743, 740, 752, but it's called a 7.5, 3/4, right? That's the nominal basic size. The -10 means there's 10 threads per inch. Okay. So there's, in 1 inch, that thread form makes 10 revolutions. So if it makes 10 revolutions in 1 inch, how far apart is each thread form? What would be the pitch of that thread? Can anybody tell me? There are 10 of them in 1 inch. How far apart are they? That's right. 0.1, right? 0.10. Does that make sense? Good. And so the series is the next thing that we specify: UNC, UNF, UNEF. So the UNC is unified course threads. Okay. And then we have the class. This one happens to be class 3, which is high precision. So if you're thinking in terms of cost, do you think a class 2 is going to be more or less expensive than a class 3? Less expensive, right? Most of your ordinary fasteners that you buy right off the shelf are going to be class 2. If you want specialty, you go to class 3. If you want really cheap to assemble carnival rides, get class 1. Nobody goes to the carnival. Y'all feel comfortable about the carnies putting those together and taking them down every week?
I know. I've seen too many videos of.
Okay, well, yeah. You're standing in line, you see the bucket full of spare parts laying over there.
One time, and I just started seeing the whole thing just lift up on one end, and I was like, "Oh shoot, I'm not writing that." No,
That goes through my mind all the time, but I've never seen really any of them break down, or they kind of get stuck every once in a while at some spot, but I hadn't seen anybody get hurt over the years.
Or like, I will not ride the Ferris wheel because, for one, I hate heights.
Yeah.
For two, I've seen so many videos and watched so many people get stuck on them. I would have a panic attack by this thing.
Yeah, I think I've probably been on one longer than I'm supposed to have been on one due to some kind of mechanical issues, but it all worked out all right.
Yeah, I've seen my friends do stuff very, like, swings.
Yeah.
Start going up and spin.
Yeah.
Well, they just think great stuff, and I told them, I said, that thing's gonna break down.
Yeah, I guess it happens. But I give carnies a hard time. They really do a pretty good job, I guess. So the A or B after the 3 in this case, A is for external threads, B is for internal threads. That's all there is to that.
I hope that they have it to, torque spec also.
Well,
Like,
that's
they
gonna
don't just put an impact to it.
Yeah.
Snug it up.
Yeah, and that the torque specification depends on a lot of different variables other than just the fastener, but what's the base material that's being threaded into and all that sort of things. What's the application? So yeah, that's a little different. If you were working on an assembly of something like an engine or something, those torque specs would be part of the specification, not necessarily of the bolt, but for that bolt in that particular application. And then here we've got the -LH, which means it's left-handed threads. So Those are the bits of information that you should see every time you encounter a threaded feature on a drawing. So this drawing we had from last week, and like I said, may not have finished it, and that's okay. That 972, it actually had 2 threaded holes, right? You guys remember seeing those? They were actually, let's see if I can pull it up. I think I still got it open. Yeah. How long it'll take it to come to life here. So, you know, in this problem here, we have this threaded hole and this threaded hole. So what does this mean now that you know what's going on? Somebody explain the 2x for me. What does that mean?
There's 2 of them.
There's 2 of them. Good. So somebody else tell me what the 0.25 means.
So the 0.25 is the diameter.
Nominal diameter, right?
And 20 is the threads per inch.
So if there are 20 threads per inch, what's the pitch?
0.2.
Nope.
120.
That's right. It's 1/20th. What is that? That is right. It is 1 divided by 20. And that's how you can always solve it. If you don't know, you know, this one is 50 thousandths, right? 0.05.
What, 0.02 or something?
1 over 20 would be 0.05. So, but that's how you do it. You take the inverse of that number. So 1 divided by 20, if it were 28, it'd be 1 divided by 28. And then we got the UNC, which is unified course, right? And then 2B, which means what?
It's less expensive.
Well, 2 is the mid-range, right? And a B means it's an internal hole. It's a hole. It threads in the hole. Okay. So now we know what that means. That's good. So let's go back over here. Back into this. So any questions about this? You'll see a lot of this. This is something you really do need to understand pretty well. So again, here's kind of the cheat sheet for it. I think this is in your book. You can see this in the book. So when we have external threads, we want to put that thread note onto a leader that points to the edge of the threaded cylinder. And notice I'm showing this in simplified representation. Okay. So whenever I draw this, and I know this needs to be a 3/4 inch thread, what kind of diameter do you think I should make this? What should it be? Yeah, 0.75, right? Okay, 0.75. Now, whenever I put these hidden lines in, how far down should I make it go? I haven't told you this yet. So, I mean, you know, it's supposed to represent the root diameter, right? Minor diameter. And I don't have it in here with me, but I will bring it in here. And you can look that up in the machinist handbook and make it exactly right. But you know what? It's a symbol. I don't care how far down that hidden line. It needs to be far enough down you can distinguish it from the object line, and not too far down it looks like something else is going on, right? It just needs to look about right. Does everybody understand that? Yeah. Some of y'all can tell William that whenever y'all see him. Here's the thing. Somebody, I don't know, maybe more than one of you, is going to ask me, well, how big do I need to make those threads? Or where do I put those hidden lines? And I'm going to hand you the machinist handbook and you can look them up. Right? Otherwise, you do what? You make them look right. Just make them look about like that. But that nominal diameter is the size of the cylinder. Same way with a hole. That nominal diameter is the size of the hole. And, you know, the real logic for the hole is the outside, the hidden line diameter should be the nominal size, and then the object line should be a little bit inside. Again, I need to be able to distinguish those two, but I don't really care. You don't have to. You can look it up and you can make it exactly right, but it really don't matter, is what I'm trying to say. If you look at this one that we just looked at, I don't think they looked it up. I mean, you know, in my opinion, that object line is a little too far away from the hidden line, but it, you know, it represents the symbol that that's a threaded hole. That's all you're trying to do. Does that make sense? Yeah, you were waiting on that distance, weren't you? Now you know. All right, so here's what sometimes you might have to put a hole on the profile. We typically don't like to do this, right? We generally give the diameter of the hole where it's shown as a circle. But if you have to do this, this leader needs to point directly to the intersection of the center line and the object line. So what can you tell me about this thread?
It's probably 9, it's 26,
Right?
11 threads per inch.
Very good.
It's 4 thread.
Yep.
It's- what is that?
Should be a 1B. Looks like it's a 1.8, but it should be a 1B. And then that depth, 0.8, that's talking about how deep the threads go down, which are represented by these headlines here. So this is that 0.8. And so somebody else is going to ask me, well, how far do I make this, right? How far do I make this hole? So does everybody understand how threaded holes are made? Has anybody ever threaded a hole?
Yeah, I've done it once or twice.
So the way that you make a threaded hole is that you drill first with a drill, and then you come back with another tool called a tap. And there's a few different types of taps, and the types have control. Well, there's more than a few. There's several different types of taps, but depending on the type of tap you have, dictates how much room you need beyond those threads to get the tip of that tap in there. I'm not making the part as the draftsman. I'm specifying that I need 0.65-11 threads, 0.8 deep. Okay. So the machinist who is actually making that part, he knows what kind of tap he has, and he knows how far he needs to drill that primary hole. He knows how far to drill that hole to get those threads down that deep. So that's on him, right? I don't need to specify how deep that is. I need to be sure whenever I draw holes like this, that my minor hole that's drilled extends beyond the threads. You know, what I mean by that is this line here, we need to add this gap in here between where the threads stop and the hole stops. It needs to be, the hole has to be deeper than the threads. That's what I'm trying to say. This hole is drilled with a standard drill bit in most cases, which is 118 degrees. Okay, so that's how you know what that angle is. If you're using, Inventor, and you put this blind threaded hole in there, it'll put the drill point and everything in there for you. If you're using AutoCAD, you got to draw this stuff manually. That's okay. So if we have a through hole, we don't have to give the depth. But again, notice how the crosshatch is going all the way to the solid line, which represents the minor diameter. The outer line should be the nominal size, 0.75. But if you have to hatch this, put your hatches in before you put your hidden lines that represent your threads. Otherwise, the hatch will stop at the hidden lines, and it's not supposed to. Now, we're going to talk about metric threads. So those were inches. Any questions about inches before we go any further? Does everybody kind of understand what we're talking about? Feel pretty good about it? Okay. So we're going to talk about metric threads. So this is the bits of information that is required to fully specify metric threads. So the M, as the prefixer there, indicates that it's metric. The 16 is the nominal diameter. This one, instead of having a dash, it actually has an X2. Okay, and so that X2 is not how long anything is, but it's the actual pitch between each thread form, 2 millimeters. So we don't have to do any math to figure out what the pitch is. It's actually just giving us the pitch in millimeters. Does that make sense? And then you have some more tolerance and grading. So we have, the 5G is the pitch tolerance. So the smaller the number, the tighter the tolerance. So number 5 is your typical commercial grade stuff. And then 6G is the crest diameter tolerances. And in most cases, on the problems that you'll see and that we'll work on, you won't have those tolerance designations given. And if it's not on the problem, I don't expect you to put them in there. I need you to recognize what they are when you see them out in the real world. But for the most part, a lot of our problems are just going to say M16/2, or it may just say M16. That might be all it tells us, M16. So in that case where you just see the M16 and there's no by 2 or by 1.5 or by 1.25, you use the most coarse thread available for M16. So if you're working in AutoCAD, that just simply means that your outside diameter is going to be a nominal 16. Your inside diameter is going to be something less than that I can distinguish because you're drawing that simplified symbol, right? But if you're using Inventor to put a threaded hole in or to put external threads on a shaft, then when you drop the list down, you'll see M16/2, M16/1.5, M16/1.125, and you're going to freak out and say, I don't know what to do. I don't know what to do. Here's what you do. You choose the one that has the largest number. That's the coarsest thread. So if it's 1.25, 1.5, and 2, which one would you choose? Did I lose everybody? Everybody just zone out at the same time, everybody? So again, if you just see M16, the thread that you choose out of your list in Inventor would be the one that has the coarsest thread, right? The furthest thread pitch. So if it said M16/1.25, M16/1.5, or M16/2, which ones would you choose? Which one would you choose? 2, M16/2, the coarsest thread, the biggest number. So again, here's the meaning of each digit in the thread specification. Here's the examples. And again, if you're putting that specification on an external thread, you attach it to a leader. You put the thread by the pitch, or you may see it without the pitch, but that's going to make it be the coarse thread option. Okay. If you don't see the pitch, it's the coarse thread option. So now we're going to talk a little bit about some different threaded fasteners. So you probably all your life heard of bolts and screws and all that stuff, but just a little bit more nitty-gritty definition. So a bolt is actually designed to pass through 2 clearance holes and be secured with a, usually a washer and a nut, right? Like you're seeing on the left. So notice it's passing through 2 different materials with clearance holes, right? A cap screw or machine screw is often passed through 1 clearance hole and threaded into the second material, right? So you got a blind threaded hole there that cap screw threads into. So it passes through 1 clearance hole, threads into a threaded hole. Does that make sense? Then you may have a stud that would pass through 1 clearance hole and screw into another blind hole. Does those kind of make sense? Just a little different terminology there. So threaded fasteners have different types of head styles, and that's usually one of the first bits of information that is specified is the type of head that the fastener has. You'll see smaller fasteners given, instead of the nominal diameter in the spec, they actually have a number 4, a number 6, number 10, number 12. And then we'll get into the fractional decimal sizes as they get larger. Set screws have a variety of heads and a variety of points for different applications. And we're not going to get into which type of point is in which application. And I don't think that's going to be something that you'll be tasked with as an entry-level designer. If you go to work for somebody that does a lot of rotating parts and attaches pulleys and sheaves and things onto shafts, then they've got a precedence of the type of set screws and applications they like to use. You just apply with whatever type they've been using historically. So But just know there are a wide variety of points and head styles and set screws. Set screws are used to are designed to hold things on shafts that tend to rotate. Lots of stuff there. Let's look at the problems for the week. So there's two things that I'm going to ask you to do. First, I want you to make a drawing for each of these parts. So just like you've been doing, except, there's multiple parts on this one sheet. If we look at this part one, this movable jaw here, which is this guy right here. So we got M8, 2 holes. What does that mean? Right, so that's a threaded hole, right? Everybody understand there's 2 threaded holes in that part? And the nominal diameter is 8. What is the pitch? Whatever the biggest one is, right? If you're putting that note in your drawing, it can just be M8. If you're doing it in AutoCAD, you can just put M8. If you're doing an Inventor, you'll pick M8 in the largest thread and it'll come in right. Okay, so this is a pretty simple part. Make the orthographic views for the drawing of that part. That's one drawing, right? So now if we look at the part 2, this stationary jaw, is this hole threaded? No, right? It's just a regular through hole, right? We've done that. Does everybody understand that hole is not threaded? How do I know that hole is not threaded?
There's nothing that specifies.
Right, there's no M there. It's just a diameter 8.5. What about this one over here? Is it threaded?
No.
No. This one says 6 deep. This one doesn't say anything about deep. What's going on with the 8.5? The 8.5 goes all the way through, right? If it doesn't tell us how deep it's going all the way through. The 4.8 does not go all the way through, right? It goes in 6. And so it's going to have that drill point on it. So if you do it in AutoCAD, be sure to include the drill point. If you do it in Inventor, it'll do it for you. Y'all, has everybody got their Inventor wings under them yet? Their legs where you're drawing good?
Yeah.
This would be a good one to do in Inventor. It'll take a lot of work out of it.
Question.
Yep.
That project last week, did you need to put that on there? Like through with the threads? You didn't know how to do it yet?
Yeah, I mean, we talked about how to make that look that way before we did it. So yeah. Yeah. So let's see, part 3 here. So this end actually has a diameter of 4.5, right? What should the diameter of this part of it be? 8, right? Does everybody understand that? So that's threaded. This is what's called an undercut note. And what that means is that, we got the head of the thing here. We've got a little undercut right here. And so here comes the threads, right? So this simply means that this gap here is 1.5 wide. And this diameter here is 5. Does that make sense? It's talking about the little neck end right there. It's hard to see on that, but that's what that's pointing to. The knurl, I don't want you to try, and I don't want you to use real thread forms either. I want you to use what's called cosmetic threads, where they actually just look like threads. Inventor may actually thread it. I don't remember, but don't put anything in your model with the knurl. What we'll do with the knurls, when you create that drawing and you have that piece of that head of that end that's knurled, you'll just put a little spline out here like this and put a little crosshatch in it that looks like the crosshatch is called net. And then you just put a note on it, knurl P.8. Does that make sense? So don't try to knurl that. If you cut those knurls in your model, really actually model the knurl in like it's supposed to, it'll take all your system resources away from you, and your software will move terribly slow, and Nobody will be happy with that. All right. Part 4 is very similar. Same thing. We've got, what's the diameter of this end of it? 8, right? We've got another undercut here. It's actually a groove on the head there, you know, and then this one's got a hole, and it's also got the knurl. And then finally, we're going to have, this is a sheet metal part. So all the thickness is 1.52. It's 1.52 thick all the way around. The only thing I normally see is when you bend these sheet metal pieces. I don't know how good I can sketch it here, but if you're not careful, these bends get messed up. You know, what you want to do is whatever radius, you use a real small radius here, and it doesn't tell us what bend radius is. This would be based on what kind of tooling that you have in your shop to make this part. But this radius, say this radius is 1 millimeter. Just use something kind of small. This outside radius here would be that 1 mil. It'll be concentric circles, right? The outside and the inside would have the same center point, but the radius on the outside would be this 1 plus the material thickness. So that would make that one 2.5. 2. So you just add whatever this radius is, add the material thickness to it to get that outside. And so the same thing would go here. You know, a lot of times I see people just put the same size fillet on the inside and the outside, and that doesn't maintain a uniform wall thickness. It looks wonky there. So that's about the only thing you have there. And then there's one last part that we don't have any drawing for, and that's this Philister head machine screw. It's an M3 that's 10 long. You can bring that right out of the tool library if you want, or on the problem. I think I give that to you. You know, or on the problem, I've actually got it here where you can download it. So you can just download that screw and drop it right into your assembly. So first part is part A, which is where I'm asking you to create those 5 individual drawings. That's the 2 movable arms, the 2 screws, and the sheet metal bracket. You don't have to do anything with the Philister head on this first part, but there'll be 5 drawings that you'll turn in for 20 points total. And then after you model those parts, I want you to assemble them. I want you to create a front view and a top view of the assembly, including the screw, and, you know, add balloons and a parts list to your assembly. So that's another assignment. Does that make sense? 5 individual part drawings of those simple parts, plus the assembly of all the parts put together. So if you're doing it in AutoCAD, you know, you got to change, you know, object lines to hidden lines where they're behind one another or whatever. So there's, you know, quite a lot of work to do there. If you do it in Inventor and assemble it all together, it all just kind of happens nicely. So this is one where Inventor will definitely take a lot of work out of the project if you're ready for it. If you're not, that's okay. You can do it in AutoCAD, but it's a little bit more work. Any questions about what I need from you this week? And then, of course, I think we got another social media post, so don't be forgetting those. I think I'm going to add TikTok to the list. Y'all got some TikTokers?
Yeah.
Chad, you doing some TikTok? Nobody's TikToking? So I think I'll add TikTok to the list. All right. So if there are any questions, I'll get my screen out of your way and you can get back to it, pick up wherever you're at and keep moving forward. If you have questions or need some help, please do ask and let's get things moving in a good way. All right.